Hello students, welcome to lecture third. Okay, so in yesterday's class we have seen the instrumentation diagram of that is your DTA, that is your differential thermal analyzer. Okay, so this DTA, whatever the instrument we are using, it is also called as differential thermal analyzer, and as in the previous video we have seen that it consists of sample holder. Okay, this is important, sample holder. Then you can see furnace is there, furnace, which is also called as a heating device. Okay, then we can see that a thermal program is present, thermal program is present, and a recording system. Okay, so these are the four different you can say uh, the instrumental parts which present in the differential thermal analyzer. Now if you see the working of this DTA, it's the sample and the reference. Usually we are taking here sample and reference we are taking in this case, and they are placed symmetrically uh, in the furnace. Okay, they are placed symmetrically as we have seen in furnace. Okay, in yesterday's video, in the diagram we have seen that how the thermal and the reference and the standard cuvettes or the holder, sample holder, are placed symmetrically to each other, and the furnace is controlled under a temperature program. Whatever the furnace is there, it is controlled, okay, under the temperature program. Okay, so programmed temperature, and the temperature of the sample and the reference are changed, so it is varied. The temperature of sample and reference are varied here with the help of temperature controlled machine. So this is what it has been done, and during this process the differential thermocouple is set up. So when we do this system, so there is a differential thermocouple is set up. This is important. Okay, so when we do this, there is a differential thermocouple is set up to detect the temperature difference between the sample and the reference, as I have stated in the definition part of the DTA in the previous video. So this is how the working of this instrument is takes place here. Now if you see the sample, whatever we are taking, it is amorphous in nature. Amorphous means powder. We have to take amorphous nature in a powdered form, and the reference where we are using is a inert material, so which is made up of alumina, sometimes glass beads. Okay, alumina, glass beads, silica, etc. So this is how the reference material, which is inert in nature, composed of. So this is how the working we started. And now if you see the graphical presentation of this DTA, so we can show in this way. So here I will take it as like this one, then I will take a dotted line here. We will learn what is this dotted line is reference here, and slowly you can see here like this. So like this somewhat you will get it here, and you can take this as a melting point of sample. Okay, and if you see the XY recorder here, so this is the time versus the temperature here. Now this thick line what we are using here, so this represents that of the furnace, and the dotted line whatever we are using is a reference, and this final line, the curve line what we are seeing is that of the sample. So this is how we can show it here. Now this is output of a potential, whatever we are going to get, this is the result of output of potential. Okay, so this is important here. So with the help of thermocouple, so as we vary the temperature, so this is the result what we are going to get here. So this is a plot A. If I take it here, now what is this? This shows the temperature change of a furnace. I will write here, this graph show temperature change of furnace. Okay, the temperature change of the furnace, the reference and the sample against time, reference and sample against time. So this is what about the graph, this graph shows, that is showing the temperature change of the furnace, reference and the reference and the sample against the time. Now if you differentiate this, I can take another graph here like this, because it's a differential thermal analyzer. Now this is a regular. Now if I go for differential, so I will take it here like this, so time. Okay, and if I go for here, the same thing, I may get it in something like that, like this. Okay, so this is how we get here, and this part downward, so this is your melting of the sample, we call it as endothermic. Okay, melting point of the sample, and this part we take it as a exothermic. This part is a exothermic process. So this is what the differential, and this is same thing, temperature difference and versus the time here. So now if you take this B graph, it is nothing is showing the change in the temperature difference. This is shows the change in temperature difference. Okay, the change in the temperature difference, that is denoted by delta T against time, against time. Okay, so this is what detected with the differential thermocouple, detected with differential, detected differential thermocouple, detected with the differential thermocouple. So here the delta T, whatever we are going to get, so this is referred to as DTA signal. So this is referred to as DTA signal. Okay, so so like this you can see that the two graphs whatever we are using here, so we can see that the how you can see the furnace, we are having the atmosphere, so which is coming the constant here, and reference also we are taking the inert in nature here whatever, so definitely the somewhat it is coming to the furnace here, but a little straight line. But whenever the sample is been considered, so whatever we are going to get is a perfect the sample here, but whatever we are going to get the two signs here, the downward peak and the upward peak. Now this here, this we get downward peak here, because as we increase the temperature, the sample it gets into melting point. So that is a melting point of sample, and slowly it increases, and there is a increase in the peak here. So in the differential, this we can see that this decrease in the peak is nothing but your endothermic nature, where you can see the melting point yeah, is been formed, and this exothermic reaction is the one. So after decomposition, whatever the product we are going to get, so you are seeing that it comes in a positive peak here, so that we term it as exothermic. So these two graphs is how, so this is a differential graph versus this is a normal graph, which is output of the potential, is temperature versus potential, and this is a differential temperature difference delta T against the time detected with the differential thermocouple. So this is what the two graph always usually we show in this way. So that is called your DTA differential. So the normal is differentiated with respect to time here, and this is how we can see a small changes which are as chemical and physical properties of the sample upon temperature variation, so can be obtained here, can be judged here what is going to happen. So exothermic, endothermic, oxidation, reduction, so like this the potential as per the nature of the sample, we can see the peaks is going to be arised here. Now if you see even for the polymeric nature, because one of the application for this is the polymeric materials, the DTA also is very important here. So now if you see here the temperature and the delta T signal here for, so you can see that something you can get here in this way, okay, like this. then finally it coming to downward here. So now here, so this we call it as a TG. If TG means is a glass temperature, glass transition temperature, okay, because if we are using the polymeric material, so definitely, so this is how we can help DTA, and this we term it now as a glass transition temperature. And you can see, so first peak we are going to get here, this is crystallization, peak of crystallization. The polymeric form is now crystallized as we increase this temperature, and slowly you can see here again there is small here, and again there is a negative peak here, and lastly you can see this is a decomposition where all decomposed product is decomposed here, and you can see in this case, so there is no oxidation taking place here, okay. So you can see, so here there is no oxidation, but this is your oxidation peak, and here you can see no oxidation. So like this reduction oxidation peaks, so you are going to get here. And if you see this part here, so this here part we can take it as endothermic downward, and here we can take it as exothermic, okay. So this is endothermic and these are the exothermic. This is oxidation and this is a reduction type of peak, so we can consider in this. And TG is usually referred to the glass transition temperature wherever there is a rubber type material, okay. This is very much important, and there is no absence of no evolution of heat. So if there is no evolution of heat, then we take a delta H is equal to 0. And second, if you see crystallization, so always in the heat is increased here. So heat is increased here, you can see, that's why it is coming the up peak here. So in the crystallization process, so always delta H is not equal to 0, it is having increased J. And the third what we are seeing, that is down peak, we are seeing the down peak here, and this we can show that it is endothermic process, it is having the endothermic process like this. Now this DTA is used as we said, so various physical and chemical changes is going to take place in this way, and this is how with the help of DTA we are going to analyze the changes. Now if you take one example of DTA, differential thermal analyzer or analysis for the calcium oxalate CaC2O4 calcium oxalate monohydrate and calcium oxalate monohydrate. Now one we will go for this graph of DTA, so we will take in this way, okay. So XY recorder, so you take it as a temperature, and here we will take it as a start from the 0 here, and downward you know that it is endothermic, and upward of this we know that is exothermic, and you will get in something like this, something like that, okay. So I will name it as A, and this I will take it as a B, and this I will take it as a C, okay. This is how we are going to get here. Now this is temperature as we increase. Now here the graph it is giving in this, you can see here reduce the two endothermic A and B here, so you can see here, so this A and B you can see here, so it is going to give graph to endothermic peak, downward peak you can see, that is your A and B, okay. So A and B, so you can see that two endothermic peak you are going to observe here. Now A, after heating around 200 degrees centigrade, I can take it here around 200 here. So after heating at 200 degree centigrade here, calcium oxalate monohydrate changes to calcium oxalate, and water gets evaporated because above hydrogen above 100 degree centigrade. So what will happen here, calcium oxalate monohydrate what we are taking here, so what will happen, it will change to calcium oxalate CaC2O4 plus H2O. So this is evaporated here. So this is very much important in the first case, that in the first case, in the A case, you can see above 100-degree temperature, that is around 200, calcium oxalate monohydrate is going to convert into calcium oxalate, and monohydrate is going to happen here. So this is what about the changes in the A what we are observing here. Now in B here, so what is observed here is the calcium carbonate is converts to calcium oxide here. I will take it here. Whatever the calcium carbonate, calcium oxalate, whatever is happened, we are going to get here. Uh, yeah. So before this, definitely we'll take the reaction of this here, calcium oxalate monohydrate, okay, and the reaction here follows is when it is heated in the presence of oxygen, you are going to get calcium carbonate plus 2 moles of CO2, okay, 2 calcium, you can take it as a 2 here, I think 2 calcium C2 4 C2, you can do it, okay. So just check it for the balancing purpose here, you can do it. This is what the reaction DTA, which comes from the DTA process of calcium oxalate monohydrate. So this reaction, so now you can see here the first reaction, first peak corresponds to calcium oxalate monohydrate, to this case where calcium oxalate is taking place here and water, and finally this is what happens here, calcium carbonate is CaCO3, whatever is formed is broken down, decomposed to calcium oxide plus carbon dioxide, like this, okay. So this is how it is happening here. So B corresponds to the calcium oxide, I will write it here 2, that is, this is A, and the B you can see here, in the B, CaCO3 is converting to calcium oxide and carbon dioxide here. Now what is this C? The C, whatever we are getting, says it is an intermediate, okay. C is nothing but intermediate, that is a exothermic process here in the presence of oxygen, that is in the presence of oxygen from the air, that is your oxidation, because we are doing this in the presence of oxygen. So this intermediate, we can see that this is nothing but the exothermic process which we are doing, which in the presence of oxygen, the oxygen is being referred here, and whatever we are going to get here is the two peaks, both endothermic, and these two peaks refer to the first peak for the decomposition of this removal of the water here, and the last peak is nothing but the decomposition of calcium carbonate, these two, and in between this what you are going to get is nothing but the oxidative peak here, oxidation, okay. So this is how of this compound. So this is what you have to understand. If you understand this, it becomes very easy to understand the concept of the DTA. Now we'll go for to understand this more, we'll go for the another graph of DTA of our calcium sulfate pentahydrate, copper sulfate pentahydrate, okay. So this usually the sample taken is in milligrams, 50 milligram of the sample, okay. So 50 milligram like this, in the milligram level it has been taken, and equal amount of reference also is taken, equal amount of reference sample, as I told, silica, okay, or glass bead, any of the inert material, alumina, like this. So we can take as equal amount of as a inert element, and the atmospheric maintained here is nitrogen gas as a inert, nitrogen gas is kept here, and you can see the heating range kept in this experiment is around 20 degree centigrade per minute, 20 degree centigrade per minute. So this is how the condition is maintained in the in the experiment here. So you take calcium sulfate, I want DT of calcium sulfate, now I am taking in milligrams, same amount of, I am taking reference here, equal amount of reference, any of the reference here, then I am going to maintain the atmospheric nature here, like in the previous we have taken oxygen here, so here inert nature, that is nitrogen, we are going to take, and the heating range is kept here, so particular slowly it has to go, so that is taken as a of 20 degree centigrade per minute, and this is what the condition is maintained, and the experiment is carried on. Now you can see that you are going to get this, I will take it as a 0 here, okay. So you know that what is this endothermic and this is exothermic process. Now if you see here, so I will take it here something like that. Now, like this, okay. So this is what somewhat the copper sulfate we get here. Now this is what the DTA curve for the copper sulfate pentahydrate, DTA curve for copper sulfate pentahydrate, okay. And this is your TGA for copper sulfate. This is a TGA for copper sulfate pentahydrate. So here you can see 900 degrees centigrade I am going to take here, okay. So in this here, whatever we are seeing here, this indicate complete decomposition, complete decomposition above 973 or 900, as in the previous video we have seen that copper sulfate. So we can see the complete decomposition of the copper sulfate here. Now what you are seeing here, two peaks what we are observed here downward. So this is nothing but your water of hydration, water of hydration. So this is your water of hydration. So here the TG and DTA curves of so here TGA and DTA curve of copper sulfate pentahydrate is shown here, okay. So this is very much important. So here you can see the both the DTA and the TGA curve. So TGA and DTA curve of both is shown in this figure here. Now you can see, so two peaks here, as we have learned in the previous video, that copper sulfate pentahydrate what you are taking is going to change into copper sulfate, okay. So 3H2O plus 2H2O. So here, so 3H2 and 2H2 is going to be in the form of steam here. So here this is called your at around 200 degrees centigrade, and this is called as water of hydration, water hydration, okay. So this is what around 200 degree. So you can see that the peak is going to get, and this is because of this reaction. And the second you can see here, now whatever this copper sulfate 3H2O whatever is remained here, so they further get decomposed into copper sulfate monohydrate plus 2H2 is going to happen here above 200 degree centigrade, okay. As you increase 200 centigrade about this, so you are going to see near about to 200. So both cases you are going to see here, that is your this one water of hydration. So these two you can see, this is the first case here what we are observing, this is second case you are observing at around 200 degree only. You are see the two peaks you are observed here because of these two reactions here. And finally this copper sulfate monohydrate, when you heat here above 200, it means 300 degree above, more than this, so you are going to get here this copper sulfate plus H2O like this, okay. So this around 300 degree if you heat it, so you are going to get this reaction. So these three reaction pertaining to these two peaks you can see here. So this is what water hydration we say. So these two peaks, and later on if you increase, you say, so as it goes like this, and later on if you increase more than this, so you can see here there is a complete hydration, complete decomposition of this you are going to see at somewhat in the higher temperature. So this is what about the important thing to be learned in this DTA complex, DTA study, okay. Now if you see some of the factors affecting DTA curve, factors affecting DTA curve. So the first is a sample characteristics. You take it as a one sample characteristic, okay. So in this sample characteristic you can see that the amount of sample, as I said, is taken in the milligrams, and it should be powdered form, it should be in powdered form here. And the particle size, if you see particle size of the sample, it should be small and uniform, small and uniform here. And the sample packing, if you see, so you have to mix finely powdered sample, mixing finely powder sample. Okay, so mixing of finely powdered sample with inert material, with inert material. So this is what you have to do, like aluminum or glass beads. So this is what, and finally you can see diluent is added. Diluent is also sometimes used. Diluent is used, that is your inert substance, inert material, as in the previous we have seen that nitrogen gas is being used. So like this is how the factor, this is how the main thing we are going to see in sample characteristic. So this is maintained here. So these are the factors usually affect the DTA. So whatever in sample characteristic we have seen, the powder form, particle size, small and uniform, sample packing, mix finely grained with this. So this is very much important. So if we make mistake in this sample characteristics, there will be definitely, we are not going to see the DTA curves in a good form. Now if you see the second, instrumental characteristics. Instrumental characteristics. In this, if you see now, so here the sample holder, whatever we are seeing, sample holder. Okay, so whatever the sample holder we are using, so this should be very small holder. So here small sample holder should be there, as we have seen in yesterday's video in the instrumentation part. So this small holder, so this should be made up of ceramic or glass, made up of glass or ceramic, okay, which should withstand the temperature here. And also sometimes metallic pan also can be taken here. So this is what about the instrumental sample holder, what we have to take. So here next is your thermocouple. Thermocouple, okay, this also we are maintaining here. And here the sample and reference, sample and reference. So sample and the reference, whatever we are taking here in containers, they should be in direct contact with thermocouple. They should be in direct contact with thermocouple. This is important. Okay, so and the locations of the thermocouple is constant. The thermocouple location should be constant. Okay, the location of thermocouple should be constant and adjacent to both sample and reference, and adjacent to both sample and reference. This we have seen in the instrumentation part. The thermocouple, whatever you are using, the sample and reference should be in the, they should be in the direct contact with the sample and reference, they should be in the direct contact with the thermocouple, as we have seen in the instrument in yesterday's video. And this thermocouple should be in a constant, thermocouple is constant here, location of thermocouple is constant here, and the adjacent to, and it should be adjacent to both reference and the, it should be adjacent to both the reference and the sample here. So this is what about the thermocouple. Now if you go for the furnace characteristic, furnace characteristic. Now if you see the furnace characteristic, so thermal region, okay, in furnace characteristic, thermal region, so heating rate is important here, as we have seen in the previous example. 20 degree per minute we have kept, so definitely it is around 10 degree centigrade to 20 degree centigrade per minute. This is what the heating rate is kept. Or sometimes low melting point, low melting range, low, or you can say heating range, low heating range can be maintained. Okay, so this is what about the thermal region. So where we can see the thermal regime, thermal range, so we can take it in the range of 10 to 20 degree per minute centigrade, or a low heating range can be preferred for a good good DTA signals. Now if you see the next, that is a recorder. For the recorder, you can see the speed should be the, whatever the speed for the recorder where should be optimum, should be optimum to get a very beautiful peaks here. So it should the recorder should not be kept in a very speed way, so that there is the no specific sensitivity, so it will lose. But it should if you keep the recorder speed to the optimum level, definitely there will be more sensitiveness in in the recording here. And the last one, if you see the environmental factors, environmental factor. So if you see this, so we have seen that there is two, that is we are maintaining the two, static and dynamic, static and dynamic gaseous atmosphere, gaseous atmosphere is maintained for these environmental factors. This is important. So what is static? I have seen blowing of the air, and what is that dynamic? This also is a concept of blowing of the air with the help of a compressor like this. Okay, so these two is maintained in the environmental factor in the for to maintain the gas atmosphere. So these are some of the factors influencing the DTA. Okay, so under some thermocouple and furnace characteristics, instrumental characteristic, environmental factors. So in this under this all we have learned some of the points. So which are some of the factors which gives a very good I can say the curve, the DTA signals. Hope this is more than sufficient in this video. In the next video, whatever is left for this DTA, so we will complete it and followed by the next concept in the next video. Thank you.